Okay, so today I'm going to make a second tutorial about IntuitionRF, and I'm going to show you how to use the geometry nodes feature. So this feature comes in the release 0.2, and it lets you use geometry nodes to define your OpenEMS primitives and meshing all within Blender. Okay, so let's get started. I'm going to show two examples of this. Let's start Blender. Okay, so now we have this default cube. We are going to jump into the geometry nodes environment, and we are going to start designing our antenna here. So let's remove the input, and I'm going to start with an example of a Yagi antenna. And we are going to make it all parametric within the geometry nodes group, and then we are going to define how it interacts with OpenEMS by adding some attributes to the vertices and faces with custom geometry nodes that are defined here by the plugin. Okay, so let's start by adding a mesh line like this. We are going to make it horizontal, so let's go endpoints -0.1, let's say, and then 0.1, 0. Okay, so that's our base segment. Now what we can do is, well, let's define the size first. So combine here like this. Now let's call this dipole length, why not? Okay. And now we are going to make some more of these, some copies of these. So let's do it like this. And now we can see that it starts moving. Let's add some more elements like this. And we are going to make a second parameter of this value here. And let's call this one, let's call it the spacing, dipole spacing. Okay. Okay, now we want to add, so those are all passive elements. I believe they are called orientators, orientation elements, something like that. Now we are going to add our active element. What we want to do here is actually have split it in two and have the port in the middle. So let's do that. Going to use this mesh line again. Going to use all of these. Let's use this on Y. Go. Oh, also we want to make this too, like this. Let's go from 0 to that size and then join this. Okay, so that's half of our driven element. So let's leave some distance in the middle for the port. So let's go with 0.01, should be good. Yeah, that makes a 2 centimeter wide port. And now I am going to take this, mirror it on the y-axis, and then join it. Okay, so that's our driven element. So usually the driven element is slightly longer than the other elements. We could make this a parameter of the antenna. I'm just going to make it 5% larger than the other element. So let's use another transform here and scale it on the y-axis by 1.05, like this. And actually that's not what we want, because it's going to scale the port too. So let's remove it from here, and instead multiply here by 1.05, like this. And now we still should have our 0.01 start position here and 5% larger here. Okay. And now final part is we need to add a reflector at the back. We are going to use a mesh line again, and then we are going to make it again 5% wider than the driven element. So let's use this again. Let's use the output of this. Combine. This time we are going to use it on both directions. So let's go like this, like this. Reuse this one. And join it in here. Okay, and now we need to move it back on the x-axis. So let's actually make this a parameter of the antenna. So that's our reflector distance. Make it negative 0.1, like this, and there you go. Okay, so that's our reflector, that's the active element, and that's the orientation elements. And we have all of this nice and parametric. We can move the antenna, and we will do this. Okay, now we need to add the port, which is not defined yet. Let's use a mesh line again, like this, and go. Let's actually make this a parameter as well. So combine x, y, z, make this 0.01, and then a value. And we are going to call this port width. Okay. and we can use this. On the y-axis, like this. And then again, duplicate, multiply. Okay, and now we have a fully defined antenna, and we should be able to change its shape by the parameters that we defined here. Let's give it a try. So let's say that I want a wider antenna, wider dipoles. I can do this. Let's say that I want to change the spacing between the elements. I can do this. Change the port width. I'm not gonna see anything, but it's happening. If I make the port larger than the elements, you can see it move. Let's put it back to 0.01. Okay, and then the reflector distance to the back of the antenna, like this. Okay. Now that we have defined our antenna into Blender, we need to tell OpenEMS what is what in the antenna. I'm going to save this. Like this, sorry. Call it, make a new directory here. Okay. So let's set up the OpenEMS simulation. I'm going to start with adding a default meshing line set like we did on the previous tutorial. Let's make a new collection as well, call it RF. Set it as a simulation collection. Add the default meshing line set. In this tutorial I'm going to use a scale of 1 instead of 0.001. You can choose whatever scale fits your needs. I'm going to leave it at 1. Okay. Now I'm going to scale this up so that we get the whole antenna in the simulation. Okay, and this looks good. Make the resolution quite more coarse, like this. Okay, and this is a good starting point. Now, the new features that was added, you can select an object that has geometry nodes enabled, like this, and you can set the IntuitionRF type to geometry nodes, last option here. And what this will do is it will evaluate the whole modifier stack and look for attributes within the geometry output. So if you have other modifiers here, like let's say bevel or something else, it will also be evaluated within your simulation. So now we can define our antenna within geometry nodes, and it will be taken into account. And it's also here that we define which element is a port, which element is an electrical conductor, a material, and so on. Okay. So let's start defining this antenna. The first thing that I'm going to do is defining what is my port. So I can go here, add a new port node like this. Now I'm also going to label all of these. So this is a port. Let's go like this. This is the reflector. This is a driven element. Let's call it driven dipole like this. And then this is all the passive elements. And they are called directors, like this. Okay. So let's use that node, port node, and let's put it here. And now we can define what our port does. So it needs to have a non-zero index. So let's go with index 1, impedance of 50 ohms. And we need to define an axis. Now you can't define an arbitrary vector, it will be snapped to the nearest axis. So in this case it's on the y-axis, so let's put 1 here, and then it's also going to be an active port. Okay. Now we can define everything else to be a perfect electrical conductor. So we can use this. And now we can choose whether we want the edges of the mesh, the faces, or the volume to be the conductor in OpenEMS. So in our case there is only edges, so I'm going to use edges. And now what I can do is actually split this like this, and I'm going to cut this. Okay. This way the port is not defined as an electrical conductor, so I can have my port node here, merge everything one first time, and then add the port after. Okay, and now we can move our perfect electrical conductor, put it here, and all should now be defined as metal conductors, as edges. Okay. Going to save this. Now what we need to do is define the meshing lines, and again we want to have our meshing lines that move with the antenna, which means that we can define meshing lines as parametric as a parametric function of our antenna model. And the way we do this is we add a IntuitionRF anchor into the node group like this. And now, because we have the joint geometry of everything, and we want both the port and the electrical conductors to generate anchor lines, we can put this after everything else like this. Need to tick is anchor like this. And now we should already be able to see what's going on. Let's try. Okay. And there you go. You see there is a line on every element and on every vertex of every element. Now we see those lines are quite close, and that's expected because we have this 5% increase and 5% decrease in size here. So let's try with the smoothing on like this. Okay, and that's already not bad. Now we can check that CSX-CAD agrees with what we see in the scene, so let's try like this. And as you can see, we have all of our elements, and we should have the edges like this, and we should have the port in the middle like this. Okay. Let's rename this to antenna. Change the simulation directory. Okay. And now we can try and run the simulation. So let's go like this. Okay, so the simulation completed. Now we can see the port parameters. There is a new tab here that lets you see a port defined within Geometry Nodes group, and you can see the parameters. So let's go with the S11 parameter. Okay, and now we can see that we have a strong resonance at 542 megahertz. Okay, now what we can do if we want is improve the meshing quality. As you can see, I have only meshing lines on the elements themselves, but usually near the perfect electrical conductor's edges you want to have some more finely defined mesh. So we can do that within the geometry nodes group, and what we can do is add some geometries that will be set in the output, but not define it as a conductor and just define it as a anchor. And what this will do is add the lines without changing the primitive in the simulation. Okay, so for instance, what we could do is take this output, go mesh to curve, like this, and then curve to mesh, like this. I'm going to join this here, so it will not be a electrical conductor nor a port, but it will be an anchor in the simulation. Okay, and now as a profile curve, I'm going to use a circle like this. It's going to be way too big by default, so let's make it a 1 centimeter radius like this. And then it's also going to be over defined, so let's go with a resolution of 4. And now we have these meshes. Maybe we don't want to actually have the faces, we just want the lines. So let's delete the geometry and remove only faces, like this. Okay, and now because this is used as a anchor, we can see what the smoothing does. And now, as you can see, we have a much finer resolution around the director's elements. We can do the same if we reuse, if we join in the geometry from the driven element before it's set to a electrical conductor, like this. So as you can see, it gets defined around it as well. And then we can also join the reflector geometry. Okay, and as you can see, we now have a much finer meshing around the geometry. Now we can do this once or twice depending on how many cells we want around our elements. So what we can do is make it larger on the y-axis. So let's say by 5%. And then we can join the geometry back in like this, and I'm going to also so yeah, actually I'm going to duplicate all of this so that I can set a different radius. Let's go with this, and now the radius I'm going to make it half the radius, like this, and then I'm going to transform it and make it 5% wider on the y-axis, like this. Okay, and now if we show the meshing preview, as you can see, we've got some nice meshing lines that go all the way. Now those two are close, and that's expected. It's because we have this driven element port that it scales around the origin of the object, so you get a 5% scaling on something that's not already very large to begin with, so it gets those two lines together quite close. So that's probably not what we want, so what we can do is make it 10% maybe. Okay, so that's still quite close. and probably not what we want. And then we also get some meshing that's quite close here. So maybe to begin with, I'm going to simulate again without this second meshing. I'm going to try like this. Okay, give this a try again. Okay, and now if we see the port parameters, we get a resonance at 633 and then at 655, and we actually have a quite wide bandwidth. Let's see, 6 dB bandwidth is about 30 megahertz here. Okay, let's see the radiation pattern like this. So this may take some time to compute. Okay, so it just completed. Let's scale this way down like this. Okay, and now you can see a radiation pattern which is somewhat close to what you'd expect from a Yagi antenna. So there is a front lobe, and then there is some side lobes and a weaker back lobe. Okay, so obviously this is not a very good antenna, and you'd want to optimize this. And let's see what it does when we change parameters. So we can let's say we can increase the number of directors to make it more directional. Let's try this. We're actually going to make this a integer as well, like this. So this is now a parameter of the system, and we go from 5 to, let's say, 6 or 7. Maybe I need to increase the simulation size a little bit, like this. Okay, run the simulation again. Okay, so it doesn't move very much when we add elements, so that's good. We have a bandwidth of, yeah, about 30 megahertz. We can see a dip starting earlier. Let's see what it did for us in terms of directivity. Compute the radiation pattern again. Okay. Let's scale this way down again. Okay, and that's the computed radiation pattern for our antenna. So as you can see, it's not a very good antenna, but then you can change your parameters and see how it changes with how the radiation pattern changes with the antenna geometry change. Okay, so we could, for instance, change the distance between the director elements or make it nonlinear. Okay, so second example, I'm going to make a periodic log antenna, so it's also going to be made of electrical conductor as metal edges. Now you can use phases and volume inside the geometry nodes IntuitionRF options. You can see, as you can see here, let's see if we go like this, make it a new collection, move to new collection RF and call this the antenna, like this. Okay. Okay. And now if we make this a geometry nodes IntuitionRF element like this, we should see it in CSX CAD. And nothing. And the reason we get nothing is that there is no meshing lines where his edges are, so let's fix that. Like this. Still doesn't work. Okay. Apply the scale maybe. Yeah, okay. So now our cube is analyzed as lines, as edges. If we change it to faces, we get metal planes on each face. And now if we change it to volume in CSX CAD, we should see no difference. There you go. But if we check the meshing, it's very different. So let's go with faces and check the meshing. So let's go view pec dump like this. So that's our meshing here. So as you can see, it just meshed the outside of the cube. And now if we make it a volume, we can view the pec dump again, and now it meshed the inside of the cube as well, all as a volume. You can also define it as a material like this. Let's say 3.8, and now it's a dielectric material in OpenEMS. Okay. So now let's make a periodic log antenna. Okay, so I'm going to start the same way as on the first example. Go mesh line, preview it like this. And now I know we don't see anything, and that's because, oh, it's here actually. Okay, let's remove this for now, and I'm going to go on the x-axis. So let's make it -0.1 to 0.1, and then 0 on z-axis. Okay, and endpoints, and we want 2 vertices. Okay. Now what we are going to do is actually have a set of let's call them studs or monopoles or something, and have them every second one on a different side. So what you usually have in a periodic log antenna is something like this. So you have an element here, and then you have a second element here, and then a second element here, okay, something like this. And each time the gap here gets tighter, and the length here also diminishes from one element to the next. And it diminishes in a logarithmic way. So let's model this in Blender, and then as for the feeding part, the feed point of a periodic log antenna is at the front, and what you usually have is you have all the elements of one side connected together like this, and then it goes around to the other elements like this, and then your feeding port is between those two elements here. Okay, and so the interesting parameters of our antenna are going to be our base length here. The length here is also going to matter, as is this distance here, and we also need to be able to change either the angle here of how pointy the antenna is, basically, and also, but you can also express it as a function of how long this element is, which might be easier in our meshing in Blender. We will see. Okay. And then you also might want to adjust how close together these are as a, let's say, a scaling factor on this axis, to see how this changes your antenna properties. Okay, so the first thing I'm going to do, actually I'm going to start with 0 on the y-axis like this. Let's go something like this, and then I'm going to add a repeat zone again like this, and then I'm going to join the geometry, use this. Okay, so let's start with making multiple segments on the x-axis. So translate on x, we are going to go 0.1 meter, and we are going to add some iterations to see what's happening. So as you can see now, all the elements have the same size, which is not what we want to do. So we are going to add a second transform and then scale them down on the y-axis. Let's go with a 0.8 scaling factor, and as you can see, we start to see something that looks a little bit like a periodic log antenna, but we are not quite there yet because the spacing is constant. What we can do is we can divide on the x-axis by the same amount, like this, and now you can see a basically a recursive representation of what a log is. So this is the end of the last segment would be log of base, the number of iterations of this number here, 0.8, times the size of the base segment. Okay. Let's add some iterations. Maybe we can make this a little bit shorter, so let's go half the size, or maybe even closer like this, and maybe we can increase this by a bit, like 0.5 meters, something like this. Okay, and now we can clearly start to see the shape of the periodic log antenna beginning to appear. Okay, so now we need to flip those segments, every second segment on the other side. So one easy way we can do this is rotate it by 180 degrees here. So what it's going to do is flip the whole model 180, repeat, add a new element, flip it again, and then you go and you see this alternating pattern here. Okay, now what we want to do is have these lines here, add these lines here, let's call them feed lines. But what we want to do is have them separated from one side to the other, or otherwise we're driving the whole antenna at once and we have nothing on the other side. So one way to do this is to scale it on the z-axis. So if we go with a 0.01 like this, as you can see, half the elements are at position -0.01 on the z-axis. Okay, and now we can extract our geometry parameters from here. So let's go with a combine node, make it 0.8, and then it's going to be like this. I'm going to call this so it's the log factor, something like this. Just call it the log factor. And then I'm going to call this the element count. Okay. I'm going to call this x value here call it element interval, why not? Or let's call it just a step. Okay, and this distance here is going to be the height of the antenna. Okay, so that's your height. Okay, and now I'm going to remove this here. Okay, and so that's a base parameter set. So you can go way fancier with this and have your tau value computations for your antenna within your node group. I'm going to leave it like this and just change the antenna parameters and see what happens. Okay, and for some reason the Z transform has disappeared. Let's see. Something isn't okay. Yeah, you want to scale by 1 on the Z axis, otherwise you're just flattening everything at this stage. Okay. And I'm going to reduce this value by a factor of 10, like this. Okay, and that's the base elements for our antenna defined. Now we can add the lines on the top and on the bottom. Let's do this. I'm going to call this so this is your base geometry. Now, what I'm going to do to make it easy is use a bounding box of this geometry to add my meshing lines. So let's take this output here, take the bounding box, okay. Now we combine just what we need. I'm going to use the minimum x and go up to maximum x and stay at 0 on y and z, and then add a mesh line. Okay, endpoints, 2 vertices. Okay, and now we have a mesh line that goes from the front up to the back of the antenna. Now we probably want to add some distance here and at the front too, so what we can do is add distance here. As you can see, it went on this axis, and it should probably minimum x, yeah, sorry, so that's on the other side. So let's make this a negative value, negative 0.1, and that's the distance to the back of your antenna. So let's make this a value, call it back distance. Okay. Back offset maybe. Okay, I'm going to call this the front offset, like this. Okay, and the front offset I'm going to add at the front. Let's go like this. So now if we make this a positive value, I should see, yeah, it goes ahead on the x-axis. Now what we do is we take this mesh line here, add a join here, add a transform like this, and then we are going to transform it by the same height value that we used before on the z-axis. So we have this value here, going to use a combine XYZ node on the z-axis like this. Let's add some cuts like this and translate it by this much on the z-axis. As you can see, it goes the wrong way up, so I'm going to multiply this by -1. There you go. Now we have it on the bottom of the antenna, and now we join these two together like this, and we get our lines on the top and on the bottom. Okay, now we need to add the port at the front, and we need to add a short at the back, connect those two lines at the back. Okay, so we can use that bounding box trick again. Take this output, so I'm going to call this let's call those the feed lines. And I'm going to use the bounding box again, like this. So that's your bounding box. Going to separate XYZ. And now I am going to use the minimum X and minimum Z values to define my meshing lines. My mesh lines. Okay. Now another way you can do this is dot product this input vector here by 0 on the y-axis to save a node, but I think this setup is clearer to see. So let's use the minimum X and the minimum Z, and then maximum. We're going to go for minimum X again because we're still at this point, and maximum Z. That's your mesh line. Join again. Okay, and nothing, and the reason for that, well, we need to set it to endpoints, and now we should be able to see. There you go, that's our element. So that's the element at the back, and now we have this. Okay, and now we do the same. Let's call this say stub this, and now we duplicate all of these. Take the same input here, same output here, call this the port. Okay. And this time we go from the maximum X to the maximum X, and that's our port at the front. So as you can see, one side of the port will feed the front elements, the other side, the top elements, the other side will feed the bottom elements, and then it's joined here at the back. So waves will reflect here at the back, and we can see this in ParaView and see the propagation of waves inside this antenna. Okay, so that's our base antenna complete, and now it should be fully parametric, which means that we can change its geometry and see what's happening in OpenEMS. Okay, let's see. So let's add more elements like this. Maybe make the front offset somewhat shorter like this. And I'm just designing this antenna visually. I'm not taking any kind of computation into account. I just want to design something and see what happens, and then maybe iterate over the simulation. Okay, let's save this, make this a geometry node antenna. Okay, that's the case. Now we can set the domain, scale this up like this. Let's start at this frequency, see what's going on in CSX-CAD. As you can see, there is nothing, and that's because we didn't define any electrical conductor, meshing line, or port here. So let's fix that. I am going to start with maybe with the meshing line. So let's define everything as a meshing line like this. Okay, and now if we make this quite coarse, like this. Okay, and now we have meshing lines on every element of the antenna, including on the Z direction. As you can see, there is two meshing lines here. Okay, and now we can define everything as electrical conductors except for the port element, which is going to be a port. So let's start with the port like this. Going to be at index 1, 50 ohms, axis Z, and an active port like this. And everything else, let's duplicate this, make it like this, and then everything else here is a perfect electrical conductor of type edge. Meshing line is still good. And now we can see something's going on here. I don't know exactly why. Okay. Anyway, preview in CSX-CAD, and now you can see our antenna is defined. And we can see the port element and the metal edges. Okay. So now what I'm going to do is show the meshing lines. So that's too coarse. Let's make this 0.5. Okay, so that's our meshing lines. Now you can use this lambda over 20 reference cube function, And what it does is it takes your center frequency here and adds a cube of corresponding lambda over 20 size, so that you can check that your meshing is at least as fine as the wavelength over 20, which is the recommended size for OpenEMS. So let's do this. That was not it. Add the reference cube. So as you can see, our cube is way smaller than the actual cell size after smoothing. So let's divide this by 4, like this. Okay, so maybe that's too fine. It's going to take forever to simulate. So multiply it back by 2. Okay, and this is about half the size. Maybe multiply it by 2 again. Okay. Okay, so this is about the size of lambda over 20. Now, because we have a center frequency of 500 megahertz and a cutoff frequency of 500 megahertz too, we're basically looking up to 1 gigahertz. So we will want actually half of that cell size to match for a 1 gigahertz lambda over 20 cell size. Let's do this. Okay, and that's our meshing. So as you can see, it's a quite fine meshing, so it will take some time to complete. Now we should still be able to see our meshing lines. Maybe what we can do is reduce the number of elements such that the highest end of the antenna bandwidth is not too high and we don't need too small cell size. So let's make it a 6-element antenna. Okay, and this way we can maybe make the meshing a little bit bigger, like this. Okay, and this should already be a good starting point. So now let's run a simulation. Okay, so it completed quite fast. Let's see the antenna parameters. And this is actually quite consistent with this kind of antennas, because what you get is a sharp drop at the beginning of the bandwidth, then a quiet, good bandwidth, quite large bandwidth, and then at some point you get a rejection of higher frequency. So now what we can do is try and improve our mesh, because just as in the last example, we may want to add some finer meshing around the electrical conductors. We can use the same technique and basically join everything before it gets defined as electrical conductors, like this. And now mesh to curve, back to mesh, and then we join it in before it gets set as anchors. Use a circle curve like this. Bring the radius way down, like 1 centimeter. Okay, that's still too large. 2 millimeters maybe. 4. Okay, and then a resolution of 4. Delete the geometry, only faces, so we can see what's going on. Okay, and that's our additional meshing. But if we preview it in CSX-CAD, as you can see, we don't get that meshing defined as electrical conductors. It just defines more fine meshing lines. Okay, so at this point we can check that there is no lines that are too close to each other, so this is good. Maybe you can make this even a little bit wider, like this. Okay, and this looks pretty good. Let's run the simulation again. Okay, let's see the port parameters again, and now we can see we don't have a very good antenna yet. We can see the sharp drop at the beginning, but then we get these rejections here, which is not what we want. So this is the point where we want to play with the parameters and tweak the antenna until we get a pretty good antenna. So I happen to have done this before, and I have prepared a example antenna that we can show. I'm going to run this simulation. So it's basically the same antenna, except I've tweaked the dimensions and parameters until we get a better antenna. Okay, so let's run the simulation. Okay. And now we can see something that is much closer to what we'd expect from this kind of antennas. So if we zoom in, we can see that we have a quite large bandwidth here with a rejection higher up. So it goes at -6 dB, it goes from 670 megahertz to 790 megahertz, so 120 megahertz bandwidth, which is quite good. And at -10 dB it's a little bit less, but as you can see, you still have a large bandwidth antenna, and then higher up you don't get the resonance again, and then you get some resonance further up, but basically the useful bandwidth of this antenna is around here. Okay, so I hope you found this video interesting. Let me know in the comments, and I'll see you next time. Bye.